day everyone, we are the group for Geotechnical Engineering. So we're gonna discuss the basic fundamentals of Geotechnical Engineering. So let's proceed with the topic. The first thing that we're gonna discuss is the definition of Geotechnical Engineering. Geotechnical engineering is an area of civil engineering that focuses on the engineering behavior of earth materials. Using the principles of soil and rock mechanics, this subdiscipline of geological engineering uses knowledge of geology, geophysics, hydrology, and more. There are three branches of geotechnical engineering. The first one is soil mechanics, the second one is rock mechanics, and the last one is the foundation engineering. So we're gonna talk first about soil mechanics. Soil mechanics mainly deals with soil microstructure and its property. Foundation engineering related to design of foundation and pressure distribution deals with engineering properties of soil. The second one is the rock mechanics. Rock mechanics, the theoretical and applied science of the mechanical behavior of rock. It is that branch of mechanics concerned with the response of rock to the force fields of its physical environment. So the last one is the foundation engineering. Foundation engineering is a branch of geotechnical engineering which applies soil mechanics, structural engineering, and lastly is the project serviceability. Requirements for designs and construction of foundation for onshore, offshore, and inland structure. So the next thing that we're gonna discuss is the history of geotechnical engineering, which is in the modern world.
This is the history of geotechnical engineering. So, although the exact time when humans first used soil as a construction material is unknown, the understanding of geotechnical engineering known today began actually in early 18th century. Its roots, however, can be traced back to the ancient civilizations. So first, the ancient civilization during this era, early construction around the river banks such as the Nile in Egypt and the Tigris and Euphrates in Mesopotamia actually demonstrated basic soil knowledge by the people. So the next era is the Roman. So the Romans had actually developed construction techniques using their knowledge of soil behavior and then applied it as they created roads and large structures such as the iconic Colosseum with Roman concrete that scientists still researches today about its durability. Moving on, in 1173, actually the iconic tilt of the Leaning Tower of Pisa caused by unstable soil and a shallow foundation, it actually highlighted the importance of soil mechanics. Then, in around 18th century, this is where the formal exploration of geotechnical engineering initiated. Thus, it led to the early development of theories on soil and actually rock mechanics. So moving on, Carl Tarski. So actually, he is actually referred as the founder of contemporary soil mechanics as he introduced some important ideas through his book that actually helped establish geotechnical engineering as a scientific field. So moving on to the present day, which is the 20th century, it actually introduced the significant growth in soil analysis techniques, and then it began the introduction of computer simulations that actually improved the ground methods.
BIM, Building Information Modeling, is used to create and manage data during design, construction, and operation. It helps to effectively manage resources and optimize processes in the construction industry. Geotechnical engineering is one of the complex disciplines that may require BIM integration. Various data types must be provided in a timely manner and require real-time feedback, fast processing, and construction guidance. So we have 5 fundamental rules that effectively use in geotechnical engineering. Number 1 is site investigation. Conducting soil, rock, and groundwater investigations to assess the subsurface conditions at the project site. Number 2, stability analysis. Evaluating the stability of natural man-made slope to prevent landslide and soil erosion. Number 3 is risk assessment. Assessing the risks associated with geotechnical hazards such as earthquakes, landslides, and soil liquefaction, and designing solutions to mitigate this risk. Number 4 is monitoring and maintenance. Overseeing the monitoring of geotechnical structures like dams, tunnels, and recommending maintenance of remedial actions when necessary. And lastly, foundation design. Designing foundations for structures based on soil conditions, including shallow foundations like footings and deep foundation like piles. So that's the 5 fundamental rules that is effectively used in geotechnical engineering.
Public safety. Geotechnical engineers are entrusted with the safety of the public by ensuring that the ground and foundation upon which structures are built are secure. Given the nature of their work, which often involves evaluating and modifying the ground upon which structures stand, the safety implications are profound. Quality. By maintaining the highest standards of quality, they ensure that the designs and structures we create are not only safe, but also durable and efficient. Quality continues through meticulous material selection and testing, ensuring that the materials used are fit for purpose and meet all necessary standards. Environmental responsibility. This principle is about reflecting on the duty to safeguard the environment while advancing human development. As engineers, we recognize that the work interacts directly with the Earth's natural system, and it is their obligation to ensure that these interactions are sustainable and minimally invasive. Social responsibility. This is about contributing to society by ensuring that engineering projects are designed and executed with the well-being of communities in mind. They take steps to prevent problems like environmental damage or displacement of people. They listen to and address the concerns of local residents, ensuring that project and fare are sustainable. This helps improve the quality of life for everyone affected and ensures that the project contributes positively to society's well-being. Professional integrity. It involves upholding the highest standards of honesty, transparency, and objectivity, meaning they must provide accurate and truthful information, avoiding biases that could compromise the safety and reliability of their work. Maintaining professional integrity ensures that they uphold the trust of their clients, colleagues, and the public, contributing to the overall credibility and ethical standards of the profession. Respect for profession or professionalism. They demonstrate this respect by following industry standards, supporting their colleagues, and helping the field grow through ongoing learning and sharing knowledge. They honor the commitment to quality, safety, and ethical conduct, ensuring that their work reflects positively on the profession as a whole. This is an example of a geotechnical failure in 1993 where the bridge has collapsed due to a collision with a barge. Ethical responsibilities. The first one is safety over cost. Geotechnical engineers are entrusted with the safety of the public by ensuring that the ground and foundations upon which structures are built are secure. This means recommending materials, designs, and methods that ensure the structural integrity of a project even if they are more expensive. Cutting corners to save costs can lead to catastrophic failures, endangering lives and property. The second one is long-term versus short-term. It's crucial to ensure that structures we create are not only safe and reliable, but also durable and efficient, meeting both current needs and future demands. While short-term solutions might seem cost-efficient or convenient, they can lead to higher risks, more frequent repairs, or even failures down the line. Therefore, it's essential to prioritize long-term stability and durability, even if that requires more effort or resources. This approach not only enhances safety but also ensures that the structure remains reliable and functional for many years to come. The third one is communication and reporting. Geotechnical engineers have a critical job of identifying potential hazards before they occur or even evaluate after the hazard has occurred. They are required to thoroughly investigate any issues that arise to prevent future problems. That's why clear and honest communication is essential. It is the responsibility to accurately report findings, risks, and any concerns so that all stakeholders are fully informed and can make sound decisions. The next one is infrastructure design and maintenance. As mentioned, it's crucial to ensure the design is strong and durable enough to last a long time, meaning the infrastructure should be designed to meet the required standards, but it doesn't stop there. Regular maintenance is also the key to keep everything safe and working well. Lastly, safety and precaution. This means conducting thorough risk assessments, putting safety protocols in place during construction, and preparing for emergencies. Ethically, engineers should always prioritize public and environmental safety over speed or cost, choosing to be cautious to protect everyone involved. All in all, I would say that the ethical responsibility in geotechnical engineering revolves around upholding safety standards to ensure that people can live safely. And that concludes the ethical responsibilities in geotechnical engineering.
The foundation of structure are the responsibility of geotechnical engineers. Work entails evaluating field data, developing foundations, figuring out how to guarantee slopes or foundations are stable, and managing operations on a building site. The foundations of structures are the responsibility of geotechnical engineers who frequently work for consultancies. Work entails evaluating field data, developing foundations, figuring out how to guarantee slopes or foundations are stable, and managing operations on a building site. They frequently work for advisory firms.
So that was all for our presentation. Thank you for listening.